Right, good morning. I'm Jeff Hammond with IGSHPA. Thank you very much for joining our Dig Deeper session this morning. This happens to be Earth Day as well, so it's good timing on this Dig Deeper session. We'll go ahead and get started. I have just a couple of announcements. One of them is what I already mentioned. This couldn't be better timing, really, with District Energy Systems and Earth Day. I wish I could take credit for the timing, but it happened to be the right schedule and the right speaker at the right time. So we're lucky there. Happy Earth Day. Just a few updates and some news to make everybody aware of. We try to do this at the town halls and the Dig Deeper sessions so that we can keep everybody up to date. And we're always open to any comments you may have, suggestions to make IGSHPA better. If you're looking to register for future town halls and Dig Deeper sessions, just go to the IGSHPA website, igshpa.org, and click on the events menu, and you'll find all of them listed that we have already scheduled. A couple of new items here since the last time we spoke. There's an abstract submission form on that same event page with the town halls and Dig Deeper sessions. If you'd like to speak at a future session, fill out that form and click submit, and we'll take a look at that. We're always looking for new topics that are interesting for members. Another exciting bit of news here is the business directory. If you go to the IGSHPA website and click on business directory at the very top of the page, you'll find a brand new directory. It has a lot more comprehensive search capabilities, so you can look at products and services that are offered by business members. And you can also look at individuals who might have certifications you're looking for, and a lot more going on. Just a reminder about the conference. It's in December. We're working with NGWA again this year, trying to attract more drillers into our industry as the industry grows. Exhibitors are already starting to reserve their space, so you'll want to make sure if you exhibit at the conference that you look at that as quickly as possible. And we're also getting sponsors. This next slide will give you a little bit of a preview. We already have a platinum sponsor, a gold sponsor, and a silver sponsor. We still have quite a few open. The diamond sponsorship, 2 gold, 3 silver, and 5 bronze are still available. So we'll want to make sure and take a look at that so that there are still a few of those left. CEUs and renewals. Starting in January, we're no longer waiving CEUs for renewals. Good news is we have more opportunities to collect those hours and CEUs. Dig Deeper and town halls now qualify for CEUs, as well as the annual conference. If you'd like contact hours for this seminar, please send in the chat message to IGSHPA. Sally Stevens is logged on as our IGSHPA account, so make sure you send a message in the chat feature with your name and email address, and she'll make sure that gets recorded. We're showing 0.1 per contact hour for CEUs for this particular session, and then we'll generate certificates when we get up to half a CEU. Just some housekeeping. If you would submit your questions in the chat feature in Zoom at the end of the presentation, I'll read those questions and Mike will be able to respond to those. If we don't get to all of the questions today, we'll reach out to those who still had questions. It's important to make sure you mute your microphone unless you're speaking. That's kind of distractive to the rest of the attendees. And we will be recording this session. You'll find it on the IGSHPA YouTube page after the session. All right, and as I mentioned, good timing for Earth Day. We're lucky to have with us Mike Walters from Salas O'Brien. He's a professional engineer and a lead advanced professional. Mike is an industry leader in the comprehensive techno-economic analysis of energy systems and alternatives, with a background in high performance buildings, energy planning, and the design and construction of geothermal systems and central energy plants. Walters guided Cornell University's standard-setting climate action plan, the transformation of Ford Motor Company's Dearborn Research and Development Center, and energy planning and conceptual design for the Riverlink District energy system in New York City. He has published articles frequently and spoken widely on the topics of district energy systems and renewable energy. with that, we welcome Mike and this exciting topic. All right, Mike, I've stopped my screen share. Feel free to switch over. Thank you very much.
Of course, everything on my screen went weird as soon as you did that. So just give me one short second here and I'll get this going on our side. Very happy to be with everybody today. And, you know, it's always never very fun, I don't think, to hear someone read your bio for you because it's always kind of embarrassing. Anyway, we're going to get going right now. Get this launched. Jeff, do you see that on your side? Hope so.
Not yet, Mike. There we go.
How about now? All right, perfect.
Perfect. Thank you.
Great. Well, so happy to be here. And just like Jeff mentioned here, today is definitely Earth Day. And I was doing a little bit of work before this session, and I noticed Google up on its homepage has a kind of a GIF that moves. I don't know where in the world it is, but it shows you a set of aerials from 2000 to 2020 and the amount of snowpack that's involved in that space over that 10 or 20-year time frame, and how much less is there today. And that's certainly sobering. And it was interesting because I had not planned to share that slide today, but what was my first slide was the evolution of district energy, and certainly thinking about that over a long period of time and how much change has happened in the last century, but certainly it's just been an extremely rapid change in the kinds of technologies that are being considered in district energy systems in the last decade, maybe decade and a half, and really how diverse the systems, the technologies, and the energy sources are that are being applied to current district energy situations. We see a lot of district energy applications, obviously in college and university sectors, because it's a large single owner of a lot of buildings, but also just an explosion of this approach and this kind of concept in existing commercial settings, as well as mixed use developments. And really you could think about it as heat pumps, you can think about it as electrification, you can think about it as geothermal, but there are so many technologies that are all trying to get integrated together to, of course, cost optimize and get the most environmental benefit from these systems. So today I'm going to share some large scale projects, probably some projects that many of you all on the phone call today are aware of in some degree or another. Hopefully I add some additional detail to those project examples, and then kind of try to shine some light on what makes these projects sort of viable at scale. So the first one I want to share is Epic Systems. This is, I'm always careful to say, one of the largest systems in the US. It might be the largest. I don't know that particularly matters, but it is an extremely large system that I actually am sitting about 2 miles from in my house this morning. I'm in Madison, Wisconsin, and it is in Verona. So that's just south of Madison, Wisconsin. It is an extremely large campus. It's 1,100 acres. They've slowly been buying more and more land around them. And building constantly for about the last 15 to 18 years in that location, originally with a 350-acre site, and then have slowly continued to expand that. The first set of buildings on that campus was this kind of circular set here. That was about 500,000 square feet of buildings, and done with this initial bore field that's almost 600 bores at 300 feet in depth. And those buildings were done all with small heat pumps that were distributed throughout the buildings. There were several hundred heat pumps in that set of buildings, trying to provide as much individual control and to the occupants as possible. And there were a set of issues that were addressed afterwards in the subsequent phases of the development of this campus, not the least of which was maintaining all of those individual heat pumps just through filter changes and compressor issues, and just the sheer quantity of mechanical equipment that was in those small set of buildings drove the owner to wanting to consider much more centralized systems, much larger systems to address those maintenance issues, but also to address the first field, geothermal field 1 there, was starting to heat up and was really undersized for what their ambitions on the site were. So we got engaged to do a much larger master plan for the site, and you can see kind of the outcomes of the development in the last 15 years. There's now 40 buildings on that site. They service 10,000 occupants on a daily basis to that site, and have really expanded the ground source resources, but also some large water source energy sources that are on their campus as well. You can see there's a 6-acre pond kind of in the center of that picture there, and then there's a large quarry, a lake that has been filled into a quarry to offer an open loop system there now as well. And if we look at that more diagrammatically, kind of in a energy flow diagram here, we have, you can see the lake resource on there, you can see the pond resource on here, and then there's a very large pump house that pumps 60,000 gallons per minute through the campus to essentially use as an energy exchange fluid between central energy plants that are located at clusters of buildings, and then these large energy resources that are the ground, the pond, and then this new quarry system that's up in the far right. I think that's one of the interesting things that we're trying to do in this setting is trying to maximize the effectiveness of the simultaneous heating and cooling that occurs at the building level or at the group of building levels, and then trying to exchange building energy between central plants that deal in these sort of circular clusters, and then exchanging it as necessary to utilize the ground source resources, the geothermal pond there, or the quarry system. And the pond is really used as a mechanism to control temperature in the various bore fields. So it's more of a resource that's used in the winter to continue to maintain ground temperatures effectively and provide for a readiness for the upcoming cooling system. This is an electronic medical records software company, and so they have a lot of cooling need on campus throughout the year, including some major data centers and training centers. So they really do have a lot of need for maintaining that ground temperature effectively, of course. Some specifics here on the scale of the system and the piping. This is 6,100 geothermal wells. I mentioned the first field was drilled relatively shallowly. The subsequent fields were to the 500-foot in depth, which equates again to about 627 miles of vertical piping for those of you who want to be impressed by the amount of plastic that's deployed here. And then the pond and the quarry are quite large systems as well. As 27 acres of system there. And then the overall capacity is 27,000 tons of cooling and heating. So it's a very unique system. It put us certainly through our paces from a construction logistics perspective. And we continue to build out that system there. And there is an integrated community of contractors, architects, and engineers that work on site daily to ensure that the system continues to develop in a way that is effective. I guess it should be noted here that this system does not have any glycol in it, and that's something that we certainly try to avoid in all of our systems, and certainly in our district systems, that it certainly helps with the efficiency overall of the total system. One thing to note, and some of you on the phone may be interested to follow up here with Jim Tingham, but I wanted to make note that UW-Madison is continuing to do research on this system to understand how the energy that's rejected to the ground and extracted from the ground is changing and flowing over time. So I'm just providing one screen cap of, say, the last 2 years of information that they've seen there, and when injection and extraction from the ground is occurring. And they have a lot of sensors throughout this system, and Jim Tingham has been researching it at least for the last 5 years, probably longer. So if those of you who are considering large systems or just kind of are more interested in this topic of thermal transfer in the ground, Jim is a great resource for studying these systems, and would be happy, I'm sure, to share his research in depth. The next system that I want to talk about briefly is Ball State University. Again, probably a system that many people are aware of just because of its scale. It's again a very large system with but was not a new construction project, right? It was a campus conversion from a existing steam system when coal fire boilers were coming to the end of their useful life on campus. So there it's we transitioned the campus to a full 4-pipe distribution system, chilled water and heating water, and have derived a large system there. Again, I think most importantly to note here is that the campus energy use intensity has gone from 175 kBtu per square foot per year down to 105 through implementing the transition from steam to hot water, and then the high efficiency ground source heat pumps. We did put 2 new district energy stations in this system, one on the north and one on the south. You can see in the diagram here, there's the south one, the north one is way up here, and then the large well fields immediately adjacent to both of those central energy plants, and have converted the buildings to a design heating hot water temperature of 150 degrees Fahrenheit. We'll talk about that a little bit more and show you kind of how that temperature was selected. Just very quickly on the central energy plants, the north and the south plant, they're not huge footprint plants, but relatively large in capacity with large centrifugal compressor machines that are in both instances. And then so in the south plant, there is some additional cooling tower capacity provided to ensure that the reliability of that system continues to operate effectively for the campus. I wanted to talk just slightly about temperature selection when we're looking at geothermal conversion projects and hot water projects. Really, the temperature that's selected and is an incredibly important thing, not only for the efficiency of the system, certainly the lower temperature hot water, the higher efficiency we can achieve, but making the economics of these systems work, really have to try to be careful with how much the building conversion side of that equation costs. So here I've shown a couple of projects here. We'll talk about the Miami project in a little bit here as well, but you can see Ball State was designed at 150 degrees. It actually operates at 140 degrees from a hot water supply temperature, but we've had clients in the last 5 or 6 years go as low as what I'm showing on this graphic is 120 degrees Fahrenheit, and we currently have projects in design in New York City that are as low as 100 degrees Fahrenheit from a hot water supply temperature. So really getting as close to sort of low entropy, sort of ambient systems as possible from a heating perspective. At Ball State, we really wanted to be careful about how we selected the hot water supply temperature. So we looked at initially resetting the existing systems back to 180 degrees hot water supply temperature, 150, and then even down to as low as 130 degrees. And you could see here with the number of red buildings that kind of pop up on this campus map, just setting back to 180 degrees, it triggered a couple buildings to not be able to maintain space temperatures effectively, but a pretty modest number that could be easily addressed through conversion work. And then 150, a few more buildings show up. And at the 130 degree scale, we really did see a significant amount of buildings that were going to need substantial work in the buildings to modify terminal units, to revise HVAC systems. And that was where 150 degree hot water temperature was selected to minimize the amount of money that would be deployed in the building side of this system and maximize the effectiveness of the central plant systems and what we could do there. Now, the next project is Miami of Ohio, right? Miami University in Oxford, Ohio. This is a picture of their new geothermal plant. But I really want to share with you some of the key metrics of their progression from 2010 to current and where we're headed to by 2026, and kind of the scale of how impactful a large district system has been for hitting performance metrics, not only in financial performance, but energy efficiency and carbon reduction. In 2010, their existing heating system was a steam system fed from a steam plant in the bottom left corner there of the screen. And by 2026, their campus will have converted almost entirely away from a steam system to a diverse set of energy plants. They're kind of deployed throughout the map here. There's a northern geothermal plant. There's the geothermal plant that is associated with the green set of buildings in the sort of lower left corner. and then some integrated chiller plants that also do heating and hot water. The same as it can be said for the chilled water system. Their existing chilled water system in 2010 had kind of that north and south plants feeding into the campus, and they've done the same kind of conversion process there, where they're integrating geothermal plants and trying to get as much simultaneous heating and cooling load provided by heat pumps as possible. And here, I think it's important to note that they do have a relatively balanced thermal profile for their geothermal plants, and really have a lot of very significant simultaneous heating and cooling load. They have a diverse set of buildings, which I think is a very important thing to note for all these district projects, is the diversity of loads that are available and the amount of simultaneous heating and cooling that can be provided from the heat pumps themselves without even using the ground source resource. Does provide that exceptional level of energy performance. So here you can see it's a very balanced 49 to 51% cooling and heating, and really allows for a very effective geothermal plant. So I wanted to share the specifics of the coefficient of performance for that plant. This was measured in 2018. They continue to measure that on an annual basis, but you can see in the peak of the cooling season, they're achieving a COP of almost 8 in this plant, and at the peak of the heating season, they're still well above the 3 from a COP perspective. So that obviously is going to help really drive energy reduction, and it's going to help, of course, drive cost reduction. So the set of metrics I'll share relative to these plants, it's interesting to note they're different plants throughout their campus now. Their original steam plant was only at a 0.74 from an efficiency perspective, whereas the south chiller plant that has a lot of simultaneous load associated with it and the geothermal plant are operating on an annualized basis at north of a 5 from a coefficient of performance perspective, which is just exceptional. That then, of course, flows through the cost to generate these utilities, right? So the steam plant is now their most expensive resource, and that has been certainly important for them to understand as they continue what has been a decade and a half transition of this campus from the steam system to these geothermal resources and heat pump plants. And then you can see the geo system on the far right is almost more than 2 times as cost efficient to generate utilities as the steam plant is itself. And these plants then aggregate up to show just a marked improvement in the campus cost to provide energy, right? So here on fiscal year 08, they were up at $1.25 per square foot of providing energy to the buildings. And by the time the projects are fully implemented in 2026, they'll be down to 0.7 or 70 cents almost on an annualized basis per gross square foot. So that's just wonderful progress, and it's great that Miami has been so willing to share their metrics and their measurements and keep good data and information about their progress, because it's been extremely beneficial to this adoption throughout higher education campuses particularly, but also just moving the technology into the commercial sector and mixed use developments as well. The cumulative impact of this system over since 2008 has been just remarkable. 56% reduction in carbon emissions, you can see in the kind of bottom left diagram there, and all the way down to $78 million of savings that have been generated in the last 12 years from these campus conversion projects, and they expect that obviously to continue on till their completion in 2026. I think it's just really important to note that you have to look very specifically at all of the operations and maintenance aspects of deploying these systems. It's not just about how much does it cost to drill a linear foot of geothermal well. It's about the headering cost, the chemical costs associated with their existing systems, how much water savings is derived through these systems. So we really do spend a lot of time doing as much life cycle cost analysis and sort of consulting on the operations of these systems as we do in optimizing the design of the heat exchangers and the energy sources themselves. It's extremely important to support that kind of decision making through the complete development of the project. And that work does end up kind of shifting some of the original plans through implementation. share a few slides of a current project that we're doing at Smith College in Massachusetts. There's a few aspects here that I think are useful to understand and consider as you all are exposed to your project work. Just to give you a sense of the scale of this system, it's a smaller system than Miami or Ball State or Epic. It's about 3 million square feet, but a lot of buildings, 104 buildings that are relatively small, very diverse in their building systems and their locations and their construction quality. And so there's a lot of aspects to confront through that. Also, they heat far more buildings centrally than they currently cool, right? 79 buildings are heated from a central boiler plant currently, whereas only 28 buildings are supplied by centralized cooling. And their process to get to a geothermal application was to start with considering their carbon emissions on campus and trying to figure out what their path forward would be. They made a lot of progress early on in the 2000s to reduce campus energy use and be more efficient with how they generated utilities, but then through adding some buildings to campus, they were seeing their emissions go back up a little bit. So they did some renewable energy projects to procure remote power purchase agreements with some large solar projects, and then thought the path forward for them would be a couple of ground source heat pump projects that would be major in scale. And so they started to really consider their building stock. And here you can see they're doing kind of the same process that we looked at for Ball State, which is to understand which buildings on campus have which kinds of heating systems and which systems are going to be able to operate at lower temperatures without major building level modifications. And here I think they did find that a variety of systems could be operated very effectively, setting back from 180 degree supply temperature down to 150 and even 140 degrees, and eventually did settle on 130 degree hot water supply temperature for this campus, as well as the need to add a substantial amount of cooling to existing buildings on campus to provide for comfort for the students, as well as to just simply address upgrades to deferred maintenance and other system desires as they continue to modify how the buildings that they currently have are used. The outcome of the work there was a phased implementation plan. Here you see the 4 phases of implementation and some large ground source heat exchangers that were to be deployed on their athletic fields on the other side of a Mill River, which is a relatively shallow river that would be easy to cross with a distribution pipe. That would be about, I think it was about 8 acres of geothermal fields at about 800 feet in depth. And that was the point in the project where we did look to the construction community to get involved and integrated into the project and to really assess, were there more cost-effective ways to deploy the systems that we were considering? What other strategies could we look at from a geothermal location perspective? What kinds of piping materials would we want to consider for the distribution systems? And the outcome of that was moving away from a more centralized system that would be serviced from the central plant that you can see in black here in the bottom of the screen, and moving to kind of a mini district system. And you can see this is the current plan they have there for a 6-year implementation of the planning work that we've done that took about almost the entire pandemic to get to this point. So you can see the West District in the top is primarily a residential zone with some land area available to it. There's a kind of a sloped lawn in front of this the square building here, as well as the consideration to go inside of this quad or in front of that. And that will be a ground source heat exchange plant with some air source heat pumps associated with it. The North District here will use the lawn that's next to a 100-year-old original boiler plant that will be converted to a heat pump plant there, with a geothermal field in front of it. And then the Central District is the kind of the green and yellow buildings that were phases 1 and phase 4 of the original plan. And that will have a ground source heat exchanger that's kind of off the screen to the lower left that will continue to service the main bit of campus, as well as the majority of the simultaneous heating and cooling loads on that campus. But it was interesting for us to know, because as part of the master plan work, we had considered districts, and then for a variety of reasons, we sort of moved back to a centralized supply system with ground source heat exchangers deployed over phases. And as we really priced out the project, and as HDPE prices continued to increase, and we needed to optimize the capital deployment for these systems, we really did go back to sort of smaller district systems that could eventually be interconnected, but will still offer the majority of their carbon savings that they were pursuing as part of this project. And one thing to note, I wanted to draw specifically in Massachusetts, and there are lots of activities like this throughout the country, but in Massachusetts, where Smith College is, they have alternative energy certificates that are really helping to push the market and to change the financial picture for a lot of projects, where here Smith College is anticipating somewhere in the range of $2 million a year of alternative energy credits valued to the project as they implement and generate the majority of the thermal energy through heat pump systems, both air source and ground source in this application. And both of those qualify for alternative energy certificates in Massachusetts to help drive that market. So that is one of the things that we were wanting to be very careful with, how we thought through what the current valuation of those systems, of those credits would be, but also how those valuations would change over a 30-year forecast horizon as we looked at the finances for this. The other thing I wanted to note on here is certainly in the higher ed market, but also in the commercial sector and for multinational corporations, we're seeing the social cost of carbon being embedded into the overall financial analysis for projects. And so that social cost of carbon has varied pretty widely, I would say, in the last decade. But currently, we're seeing that trend higher and higher, whereas I would say maybe 5 to 7 years ago, that price would be in the $5 to $10 a metric ton of carbon dioxide equivalent. And now the social cost of carbon is easily, for most of our clients, north of a $50 a metric ton number, and in some cases over $100 a metric ton. And so that, again, really helps you as you look at moving away from natural gas systems, decarbonizing through electrification, and then making sure that the electrified systems have renewable energy associated with it. That social cost of carbon number can really help change the paradigm for how systems are considered and which ones remain viable to move forward in the analysis. That, I think, does really drive us towards trying to consider a diverse and integrated set of energy sources in our projects. And I know this is a very ground source heat pump focused, and we are certainly continue to see extreme value in that technology and that approach in all of our projects. But to make large scale systems work out and to make them, to address reliability, resiliency, and the capital cost needs of projects, we often do see some hybrid components are necessary. And the types of hybrid components, though, is kind of what's interesting to me. They continue to change. There's opportunities related to fuel cell energy in certain parts of the country. There's cogeneration systems that could be done with turbines or with reciprocating engines. We see the need for solar thermal quite often in our projects, and certainly sewage heat recovery or wastewater energy recovery is increasingly an opportunity that is just another water source energy that the technology is there now to deploy that and to be very effective with it. And so we're just extremely excited about how these additional technologies can be considered to continue to make ground source heat pump projects a very viable cornerstone strategy, but they don't have to do all of the work and can be optimized to be effective over the long haul. I didn't mention thermal energy storage, but certainly we're seeing projects that have thermal energy storage both on the cooling and the heating side that are in tank systems, in addition to what we might be trying to do with borehole energy storage systems in a variety of different ways, depending on locations and thermal profiles. A couple of more projects I want to share briefly with you. Missouri Sides and Tech is a project that we did quite a while ago now, but I wanted to highlight it again as it's another project where it's a large system. It's a district system, but it is really deployed as mini bore fields and smaller district systems in amongst a large campus environment. Again, to a very significant amount of energy savings and exceeding all of the client's goals here. But just to give you an example of where it's certainly not a one-size-fits-all kind of deployment. Every project needs to be uniquely considered for what its physical constraints are, and certainly what the cost optimization strategies can be to make sure the OpEx savings are always there and the capital investment is appropriate for what the objectives are of the project itself. A couple of projects I wanted to give you a flavor of that are in the higher ed sector. We have been working for a long time on the Ford Motor Company R&E Center. This campus is going through a major renovation and transformation. It went through a master planning project for 3 years. It's now going through a major redevelopment and new construction. And you can see here, this is a rendering of the future state of that campus. In the bottom right corner, you can see a large thermal energy storage tank and kind of the roofscape of the central energy plant that we built for them the last 3 years. You can see here diagrammatically the R&E Center systems. That there is designed for 3,000 tons of heat pump and a geothermal system. The bore field there has yet to be drilled, and they're currently working on the simultaneous heating and cooling there, and deploying a set of gas turbines, a steam turbine, and a large chiller plant to meet the needs, as well as the thermal storage tank that I showed in the picture previously. But here, the master plan needs to evolve to get the building loads to a point where the ground source heat exchanger could be added into the future. But again, it was very much about understanding loads, understanding potential hot water supply temperatures, transitioning as much as possible from existing steam systems to low temperature hot water systems, and then just defining what technologies could most efficiently meet those energy profiles. The work there and in all of our projects ends up being pretty granular. It's not very fun to talk about energy modeling and detailed analysis, but I at least wanted to give you a sort of a sense of the kind of an analysis that is required in order to validate these systems and to get them through the decision-making process, and to make sure that the financial and operating and energy savings are all there. So this is an output of a much more detailed model that shows on an hourly basis how all of the assets that are part of this system will be deployed to meet peak concerns, to meet annual concerns, to meet daily concerns for energy and utilities, and really be able to put a robust financial model together that can either convince the owner to optimize these projects and implement them, or to, in some cases, for these projects to be taken out to sort of third-party providers to really understand what the objectives of the project are, and for alternative sources of capital or operating to be deployed to the system and the project. And finally, on that project, just a pretty-ish picture, no landscaping yet on that central energy plant when we took this picture, but that's the final project that was developed for Ford and the central energy plant. You can see the gas turbine stacks there, and we're kind of looking into the building from the CHP side, and the chiller plant and heat pump plant is kind of off to the right, and that's about 100,000 square foot facility that you're looking at there. Finally, just wanted to draw your attention to kind of mixed use, large scale projects. This is the concept design that was for a large project called Riverlink in New York City, in Queens. This is about 12 million square feet of vertical development you can see in the sort of the foreground here, and then connecting to almost 3 million square feet of lower rise, low income housing in the kind of upper side of that graphic. And the energy sources here were very diverse. Again, certainly you could think of it as a ground source heat pump system or a geosource heat pump system, right? But there's a large river source energy here. Certainly ground source is planned for underneath the building footprints here. So that gives you a lot of heating capacity that is required for these systems, but the river source energy is, again, doing the majority of the cooling for this plant. and then looking at a set of other strategies here, certainly sewage heat recovery or wastewater energy recovery as an energy source. When you have such a density of development, you can really look to optimizing the systems through those types of applications as well. And again, rolling it up to, what is the district heating and what does the district cooling profile look like? What's happening? What kind of resources are being deployed to meet these needs? And then what kinds of strategies and the scale of the strategies will be required in order to utilize these technologies and implement the overall energy profile. That, I think, is the end of my specific remarks. I'm happy to kind of have some conversation and answer any questions, and hopefully kind of a drive-by of some projects, and the scale of these implementations is enough to kind of solicit some questions and get a discussion.
Thank you so much, Mike. That was very informative. It's great having actual jobs to look at that connects the dots, at least for me anyway. Let me start with some questions. The first one here from Bob, and this is the EPIC system that you mentioned. Bob asks, how much energy is harvested annually by the EPIC system's geothermal system in kilowatt hours?
Whoa, I totally don't know the specific answer to that question, but that system is 100% ground source heat pump. That whole campus is. There is no there are no boilers on that campus. There are no cooling towers on that campus. So the entire facility is a ground source heat pump system. I didn't highlight, but I think on the slide I showed they do have 10 megawatts of wind turbines that are a couple of miles off that campus, but contractually inside their fence, and they take delivery of all those kilowatts from their wind turbines, as well as they have deployed at least so far 1.5 megawatts of solar, and will continue to add solar resources to that site as well. But if the total energy flows are of interest, I can certainly look to getting that and feed it back to you, Jeff, to circulate.
Okay, yeah, that would be super helpful if it's available, and then we can communicate that information.
Sure.
Thank you, Mike. Will asks for clarity on the water temperatures, and Brian answered that question, but I'll mention it anyway because I think some others may have had that same question on cost versus water temperature, 130, 150, 180. Do you mean a central plant output temperature that serves distributed hydronic fan coils? Brian answered, correct, Will. Coil changes at air handling units to get lower water temperatures drives up costs and potentially changing entire systems out. Any additional comments on that about water temperatures and cost effectiveness?
No, I think Brian nailed it. Thanks for cleaning up my dust there, Brian.
Very good, thank you. Will asks about the Dearborn project. It seems like it was purposely a two-step process. Number one, establish a stable heat pump network and understand actual diversity. Then two, create a geosource to meet a proven need. Is that correct?
Well, there is no end of discussion I could give you on the Dearborn project, but a lot of pretty poor information quality for the existing building systems energy use. That was one major challenge for that project. So certainly the idea to set the plant up with a certain amount of heat pump ability and then identify those loads over time was part of it. There is some real drilling challenges on that site. So we ended up with a lot of tiny caverns. We ended up with some hydrostatic pressure. We ended up with a lot of challenges. So as part of the initial exploration and the first set of bore fields that were to occur on that site, they were kind of right in front of a lot of senior leadership from Ford's offices, and there were a lot of challenges with that initial construction. So the thinking was to delay the deployment of ground source heat exchange in those locations and try to make sure that the big projects could kind of get situated and sorted out, and then we could come back later and address the potential to add geo and to optimize the financial side of the operations equation with parking lots and other spaces on campus that could be more easily transitioned to ground source heat exchanger than where we were doing it initially, which was we were drilling almost 20 feet below grade and running into a lot of hydrostatic pressure challenges associated with that. So I won't bore the group with all the specifics there.
Great information. Jacob asks, did any of these systems experience leaks?
I was going to say no right away, but I wanted to pause and see if there were in fact any leaks. I really don't think so. I think that certainly not in operation. We're very careful to do flushing and purging. We're very careful to design in strainers and everything else that can protect our systems over the long haul. But I honestly cannot say that we have any leaks in any of these systems, which is one of the reasons why we're so confident in deploying systems below building foundations and in other applications that would be very difficult to get in after the fact and fix a leak if it were to occur.
Okay, thank you. That's great news. I wouldn't have expected leaks, but that's good to hear that validation.
Right.
Scott asks, is there a standardized way that social cost of carbon is calculated?
No, but there's a lot of good research out there, and there's a lot of academic communities certainly that are considering that and have published a set of white papers on that topic. So that is something I can provide Jeff after the fact. I could send you some work that Columbia and Smith College and other universities have done on that topic to just kind of give, provide more education generally on the topic, but then, provide some substantiation for why institutions are picking the values they are right now.
That would be super helpful. Thank you. Victor asks, could you discuss lessons learned on the existing campus mechanical system review process when considering the conversion/reduction in temperature from standard temp? Also, please touch on criteria on what made a building red in quotation marks on your 180, 150, and 130 degree Fahrenheit graphic. Which information did you have available to make this decision?
Yeah, so the quick answer on that is the most effective strategy we've found to do that, and effective being defined as expedient and low cost, is to ask these building owners to do slow resets of their supply hot water temperature in the coldest periods of the year, and then expect to get cold calls and to really understand how these buildings do perform and can they meet some criteria, or that's way more effective than it is to stare at a mechanical set of drawings and try to do some load analysis and understand what the engineering side of that is going to tell you on paper. So that's what happened at Ball State. When a building turned red, it was because the supply hot water temperature was reset down to 145 degrees, and either at the control system through monitoring, or an actual person picked up a phone and called and said, look, my space is no longer warm enough to be where I want to have it. And so that's what we do in almost all of our existing campuses, is we ask for slow supply water reset to the point where the building systems tell you they can't hold space temperature anymore. And that's where we kind of draw the line. And so that's kind of a remarkable process. It builds a lot of trust with the building operators. It helps you really understand what kinds of systems they have that don't work, and then really where you have to spend precious capital dollars to improve systems to be compatible with what we want to do from a supply hot water temperature. I hope that answers the question. I know there's a lot of nuance there, and feel free to reach out and we can follow up and discuss that more.
Thank you. That's great to have that comparison to real time on an existing building. Bob makes a comment, in general, it would be vastly easier to talk to policymakers if we used units of measure that they understood, like kilowatts and kilowatt hours, millions of BTUs per hour, MCF, furlongs, et cetera. Make it hard to compare heating systems to other energy systems. Let's take the lead from the rest of the world and use standard measures of energy. Please, any comments on that?
I agree. I mean, I think it's one of the worst things about learning this profession is to sort out the terminology and all of the different units that people that prefer to talk about or want to talk to things about. And yeah, I couldn't agree more.
I know my classes at Purdue were in metric, and I had to relearn everything when out in the real world. Cameron asks, you mentioned an operation/maintenance savings by going from a distributed in-unit heat pump system to a central plant approach. Can you quantify a percentage maintenance savings? Just trying to get a sense of operational impact.
Yeah, that's I mean, the EPIC system is remarkable. I think I made those comments when I was talking about the phase one of EPIC to the eventual full build out there. EPIC had I think they had 5 or 6 staff that were maintaining and operating that first campus. And when they moved away from that system to a central system, they essentially are operating their entire geothermal system and their distributed CEPs with one person in one control room. I mean, their central energy plants are dark. You go in there and there's no people, the lights are off. It's kind of beautiful. But you know, on the college and university side, we generally see you know, it's difficult to talk about that with a lot of building owners because it ends up being a staff reduction, which is kind of a not helpful politically, but from a cost reduction standpoint, the potential is there to reduce the FTE cost by 1/3 or more.
Oh, that's substantial. Victor asks, which software or softwares do you typically use to evaluate energy performance in geofield design?
Should I give away all our secrets there or not, I guess? We certainly use GLD a lot on the ground loop design side. We use a lot of custom analysis too. We do a lot of spreadsheet work. We have been more and more using a tool that was developed at the University of Wisconsin called Transis that was developed in the 70s. And we use it almost on every one of our district energy projects now because you build the system like you build it in the real world. If there's 500 feet of pipe somewhere, you put 500 feet of pipe in your model. And there's a high barrier of entry on, you know, learning how to use that tool and use it well. But it's extremely powerful to optimize how effective an energy source can be. For instance, that Riverlink project I showed, you know, we were thinking we were going to need a lot more ground source heat exchanger because we didn't think we could get enough heating capacity out of the river as an energy source. And using Transis really helped us prove how effective the river could be in really maximizing that resource. And so that's certainly an underutilized tool, I think, generally, and it's not easy to use. So I get it, but we use that a lot.
All right, thank you. Bob has another question. How can we scale the process? Each of these projects seems to have taken multiple years of study, but if we want to do something like, in quotations, convert New York City's gas system to geogrids, we won't be able to spend years on each building. How do we scale this process to thousands or millions of buildings?
Oh, it's a great question, right? I mean, I guess, Jeff, we were talking about it a little bit before the session started. I mean, there are so many barriers to moving quickly on these topics, and it's all about, I mean, it's not about the technology or the energy modeling or those kinds of things. It's about the number of humans that are skilled in doing this stuff and can be deployed to support decision making, to do the upfront analysis, and then to actually do the construction work. You know, there's only so many drillers, you know, and there's going to be an enormous amount of pressure, I think, because the opportunities are extremely large, and everybody seems to want to do it right now. So I think that the desire has clearly accelerated. The sort of human factors to implementing these things is super difficult. Back to the question about, you know, nomenclature with respect to policy, right? I spend a lot of my time now talking with state and city governments, trying to educate the policy side of this equation so that there are far less barriers to moving these projects forward, just purely from a real estate development perspective, let alone the energy system side of these projects. So that is not an answer by any means, I would say, but I don't mean to discourage anyone on the call from that. I think that everybody needs to stay very engaged and push as hard as possible, and certainly look at this as a gigantic opportunity and not a challenge per se.
Thank you, Mike. I think it gives us an opportunity to all work together, consistent message, and certainly IGSHPA and Geothermal Exchange Organization are willing to help out however we can with making sure we send the right message. All right, we have just a little bit more time. Those are all the questions at this point. If you have any other questions, feel free to type those in the chat. I'll be happy to read those. Give everybody just another minute or so. Mike has a hard stop here at 1:30, so we don't want to keep him from the next engagement. More district systems are in the works, right?
Or everybody else. I'm sure everybody's got a meeting.
All right, and we have time for just one more question from Victor. In summary, what are your top lessons learned from these case studies?
It's a tough one right at the end. I think my biggest lesson learned is you can't go into any project thinking what you did last time is what you're going to do this time. I mean, there's always something to take from the last project, but every site is pretty unique, and that's part of the part of the expediency of deploying all this stuff is you got to really understand each unique situation and what's going to make the project objectives there most effective and that you can reach them. It's the capital side is such a barrier, and I am amazed at the amount of geothermal and mechanical engineering that goes into these projects. There's at least that much financial engineering that happens on these projects, and you really got to respect that process, coordinate with it, integrate in it as far as you feel comfortable doing, and really try to be helpful there, not just say this is the one way that we can see it happening.
Great advice. Well, thank you so much. I appreciate everybody's attention this morning and participation. Thank you, Mike, for the great presentation. Hope everyone has a great weekend. Take care.
Thanks very much for the opportunity.